Since we're talking about gravity, it makes sense to stop now and talk about why we have tides on Earth. Here's an image of the Earth, and this blue circle is supposed to indicate there are oceans there, there's water there. Obviously, my drawing is not to scale. Well, what happens when we introduce other bodies like the moon and the sun? They have a gravitational pull on the Earth, and it makes the Earth want to change its shape. The Earth is a fairly rigid object, and it's hard for it to change shape, but the water that surrounds the Earth, it can move much more easily, and its shape changes to reflect the gravitational pull of the moon and the sun on the Earth. If the Earth, the moon, and the sun lie on a line, and it doesn't matter whether the moon and the sun are on the same side of the Earth or whether the moon is over here, as long as all three form a line, we get our maximum tides. And that's what I'm indicating here. There's a pull, and the tide, the water is deeper here than it is at these other locations. And let's think about why that is. It has to do with the fact that gravity follows an inverse square law. It drops off as 1 over r squared as you move away from an object. That means that the farther away you are, the less force of gravity. And the Earth is a fairly large object. So on one side of the Earth, closest to, let's say, the moon, the force of gravity from the moon on the Earth is much stronger than on the other side. So what would happen if our object has forces that are different on different sides of it? Let's say I had a spherical ball of jello, something that could move and deform a little bit. And I pulled on every part of that ball with the exact same force. The whole ball would remain a nice spherical ball. The whole thing would start accelerating in this direction. Every part of the object feels the same force. But now I'm going to pull on one side with a bigger force than I'm pulling on the other side. Well, as I pull on that ball of jello, what happens? One side gets a bigger acceleration than the other side. So my spherical ball turns into an ellipse as I pull on it, and it becomes elongated. That's what I'm trying to show here. Instead of the Earth having a nice spherical shape, it wants to turn into an ellipse because the Earth is being accelerated by this force, being kept in a circular path around the sun. Maybe this will help. If I have a shirt and I pull on every part of the shirt with the same force, in that direction, the whole shirt moves in that direction without changing shape. But if I pull on this sleeve with a big force, and I pull on this sleeve with a small force, well, as I pull, my shirt becomes stretched, and if I keep that up too long, my shirt's going to rip in half, isn't it? That's what we call a tidal force. When the force is different on one side of the object than it is on the other side of the object. Now, some of you might be very familiar with tides, especially if you're a surfer. You might check your tide charts and know when the best time to go surfing is. Some of us might not be as familiar with tides. Which body has the bigger effect on Earth's tides, the sun or the moon? Which body has the bigger force of gravity on the Earth, the sun or the moon? Well, the sun's interaction with the Earth is a much bigger force than the moon's interaction. The force between the sun and the Earth is much bigger than the force between the moon and the Earth. But the moon actually has a much greater effect on our tides. And the reason is that the moon is very close. Again, my drawing is not to scale, but the sun is very far away compared to the moon. So let's take a look at why closeness counts when it comes to influencing tides. So if I'm a distance r away from some object, I feel a force F sub 0. I know if I'm twice as far away, my force is going to be 1/4. And I know if I'm 3 times as far away, it's 1/9. And 4 times as far away, 1/16. And 1/25. Something like this. Well, I'm hoping that this helps you see why closeness counts. So let's say my Earth is this big. Now let me take my Earth and I'm going to put it over here. In this case, the Earth is interacting with an object that's far away from it. So one side of the Earth is feeling a gravitational force here, and the other side of the Earth is feeling a gravitational force here. And this is the delta F on the Earth. One side is feeling a force that's a little bit less than the other side because it's far away from the object it's interacting with. So it's on the flat part of this 1/r² curve. The delta F is not that big, even though the force of gravity from this object might be really big acting on our object. Because we're so far away, we're on this flat part of the 1/r², and the delta F, the change from one side of the Earth to the other, is not that big. But if the Earth was much closer to this object, maybe the Earth is over here, and one side of the Earth feels a force that's this amount, and the other side of the Earth feels a force that's this amount, then you can see that we have a delta F from one side of the Earth to the other. The change in force is much bigger in this case, even if the total force from this object on the Earth is less, like it is with the moon. The moon's force of gravity on the Earth is less than the sun's. But because we're so close, we're on this steep part of the 1/r² drop-off. We get a big delta F across the Earth. The force from on one side of the Earth and the force on the other side of the Earth, due to its gravitational interaction with the moon, is much bigger change, a much bigger difference than that from the sun. So the Earth-moon interaction causes bigger changes to our tides than the Earth-sun interaction. And we get our maximum tides when everything's lined up, when the moon and the sun are both pulling in the same direction. We get our minimum tides when the moon is over here, and the moon is pulling one way, and the sun is pulling the other way. We would get our minimum tides. And why do the tides change? Let's pretend we're looking down at the North Pole of the Earth, and the Earth is rotating around the axis. Let's just pick a point on Earth. We have a point over here, just some arbitrary point. And as the Earth rotates, that point moves into deep water, right? Through thick water, deep tides, high tides, we would say. And then it sweeps out and goes through a location where there are low tides. And the Earth keeps rotating. The water is always bulged in the same direction. The Earth is rotating underneath that. And then you get to a point over here where you're at high tide again, and the Earth keeps rotating and you get to a point over here where you're at low tide again. So I'll mark here would be high tide. These points would be low tides. Every day the Earth rotates once in a 24-hour period, and we go through 2 high tides and 2 low tides.